Okay, so where we left off last time was with 1D motion and talking about very simple things, position and displacement, which is a difference or a change in position. What I'd like to talk about right now is velocity. Okay? Now, velocity is a word that we've all used before, and in a physics sense, it more or less resembles the definition that we have in our minds about velocity. How fast is something going? But in physics, we want to be a little bit careful about our definitions so that the mathematical model that describes the world around us, right, the physics that we're going to apply, can characterize this important quantity accurately. All right? So, first thing we'll talk about is average velocity. Okay? So, I've spelled it out here, but also when you see the following symbol, now the V is in a little bit of a funny font here. It's the default for PowerPoint, but the important thing here in this symbol is that little bar over the top. All right? So if you see a V with a bar over the top of it, you can know that I mean average velocity, but usually I'll just spell it out. All right? So a velocity is a displacement over the time during which that displacement occurred. In other words, it's the rate change of position. All right? So displacement is a change in position, and velocity tells you how quickly or over what period of time that displacement occurred. And you can see that in the equation here, right? We've got a displacement on the top. We've got delta t, so a change in time on the denominator. And I've written out what those things mean here on the right-hand side of the equation, right? Now this graph is meant to give you a few examples of how we might compute average velocity, right? If we know the position of an object at this time, so we'll start our stopwatch there, that's 0 time. And then 3 seconds later, so time goes on, and 3 seconds later, this object has covered, it looks like just over 5 meters on the y-axis, okay? Well, this part is delta x, okay? And this part is delta t. So rise over run, right? And that means that the slope of this line, as you say here, okay, or as I say here, I suppose, the slope of this line, this dotted line that I'm connecting the two bits of data with, right, our initial time in position and our final time in position, the slope of that line represents the average velocity between 0 and 3 seconds, all right? And if we gather more data, right, if we take another reading of our position at another time, so say we have an object that first goes one direction out about 5 meters and then comes back about 3 meters, it looks like, right? So we go down to about 5-ish there, and then we come back to about 2 there, right? So first we go out 5, and then we come back 3, right? So from 5 to 2. And all of that is occurring over 4.5 seconds or so here on the x-axis, if you look at those 2 points, right? But if we were just interested in the average velocity between 3 seconds, right, that second data point, and 4.5 seconds, so this third data point here, well, the slope of this line would represent the average velocity, so this line right here, okay, would represent the average velocity between 3 seconds and 4.5 seconds on our time axis, right? And if we were again interested in what the average velocity of the object, whatever this is, between 0 and 4.5 seconds, well, then that would be the slope of this line. Because we wouldn't care so much when we're talking about average velocity about what's happening in between. We look at the final position, we look at the initial position, and we look at whatever the final time, wherever we stop our stopwatch and wherever we start our stopwatch. And we can figure out what the average velocity must have been. Okay? Now, there's a few things to say about average velocity. One, obviously, it does not represent all the details about an object's motion, right? If you were just to look at the average velocity of this object, right? If you erased everything you knew about what happened up here, right? And you just looked at the initial position in time and the final position in time, well, then this would tell you that an object moved in a particular direction 2 meters over 4.5 seconds. So let's see, average velocity 2 meters. So 2 meters minus 0, because it started at 0. And final time is about 4.5 seconds. And initial time was 0 seconds. And that gives us 2 over 4.5, which is 4 over 9. And so, 4/9 meters per second, okay, in terms of average velocity, okay? Now, a couple of things here to note before we keep discussing average velocity and sort of how we get some more detail back if we wanted to know what was happening in between. One, meters per second, which I've kind of stuffed in right there. But if you look at this equation, well, if we look at the units of the things on the right-hand side, well, the fundamental unit of displacement, length, is the meter. And the fundamental unit of time is the second. So delta t would be measured in second. So meters per second is what our unit for average velocity would be, okay? That's the standard unit. Of course, you can denote velocity in all kinds of other units, but if you're reducing it down to the standard units that we'll be using in physics, meters and seconds, it's meters per second, okay? So, the other thing is that the picture could be considerably more complicated than this, right? If we wanted to, let's see what we got here. Yeah, this is a good example. If we wanted to look a little more closely, right, if we just looked at, say, time 1 and time 7 in this curve where we're plotting position of the object versus time of the object, well, then the object would be moving backwards, right? It would be going from larger position to lower position, maybe backwards in our coordinate system, okay? Or to the left or to the right or whatever it happened to be, but moving in that direction, okay? From greater position to lower position. And we would see none of all of this changing position in between. And so when we talk about more granular information about velocity, right? If we want to really look at what an object is doing over time, well, then looking at a graph like this is really important. And in mathematical terms, what this does, if we want to know a velocity of an object from instant to instant, well, then we take the limit as delta t goes to 0. In other words, we make the little difference between the final and initial times as smaller and smaller and smaller and smaller and smaller. And that will get closer and closer and closer to telling us what the velocity is in some tiny little window of time, okay? And then we can more accurately know what's happening to an object at any particular moment. Burn me. There you go. I'm going to figure this out one of these days. There we go. Okay, so I'm going to clear the pen markings. Okay. In calculus terms, what this is a derivative of the function of position. So if you know what the position of an object is doing over time, then you can take its derivative and find out what its instantaneous velocity is at any moment in time. We're not doing derivatives here, but if any of you have a little bit of background there, that's a side note. So let's look at the question here. What can you tell about the velocity of the object at each point? So 1, 2, 3, 4, 5, 6, 7. Positive, negative, 0, larger, smaller. Okay, so remember that whether or not you're looking at the instantaneous velocity or the average velocity, you're still looking at a slope. Because as we've plotted it out, right, this delta x is a rise, and this delta t is a run. Okay, so rise over run, that should ring a bell from your mathematics background to tell you that that's going to tell you about the slope. And so the slope of an x versus t graph, right, is going to be the velocity at a particular point. Okay, so let's take a look at a couple. Let's see. One, well, remember to figure out the slope, you kind of look at the line tangent to a point on the graph. I'm not drawing it particularly well, but we can tell that that's pretty steep and it's positive slope, right? You're increasing your position. All right. That's pretty steep, so it's a large slope, so a large velocity at this moment in time. And then at some point, this object, well, it's going very, 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 very fast, but then it starts hitting the brakes, and eventually, once we get to 2, it has come to a stop, right? The slope of that line is 0, that is tangent to the curve there. And so for a moment, whatever object this is, perhaps a car, has come to a halt, and then apparently very smoothly kicked it into reverse and started going back down the other way, right? It's going from a larger position to a lower position, and it decreases its position. So all along here, right, if we had points in there, we would say they had negative velocities, because negative slopes. But here at 3, well, we again have a situation where the slope is pretty darn close to 0, so it's stopped again. So it's gone forward, stopped, thrown it into reverse, gone in reverse for a little while, stopped, and then it kicks it back into forward, and it really accelerates hard, and it gets up to a very high velocity, right? We have a big slope here, not vertical, but a really high slope at number 4. And then it slams on the brakes, and we eventually get to 0 velocity again here at number 5. Then it kicks into reverse again, coming down negative, but a little more gentle of a slope than either 1 or 4. And then again at 7 comes to a stop, perhaps a little more gently. So stopped. And stopped here, and here, and here. At least for a moment. Okay. So, I mean, this is just a made-up example, pretty abstract. I started talking about a car and going in forward and reverse, though it would be very difficult to do it so smoothly as to just be stopped for an instant and then automatically be going, and then very smoothly be going in reverse. But hopefully you get the idea and how this mathematical definition of average velocity and its extension to instantaneous velocities pertain to this graph and the motion of objects in general. So next time we'll talk about acceleration, and we'll have covered the big 3 in terms of the motion of objects: displacement, and change in position, velocity, and acceleration. So thanks for listening, and I will see you next time.